I don't think anything happened that I don't think I missed any emails about the university canceling classes today. So we're still all set to get going.
Okay.
Well, I think we can officially start. Welcome back, folks. Looks like a small class today. I'm not too sure if there's something going on with other classes. I guess this is a pretty common week for exams on week 5. But even if it's a small class, we'll still get going as normal. I'll just assume people are going to go back and watch the recording. Well, any questions at all, folks, to start us out today? Okay. Well, we're in a really pivotal spot on the course. We're at the point where we're changing from chapter 2, which was all about limits. 2.5 was just a little bit further information about limits, to finally getting on to more interesting things and defining the derivative. So chapter 3 is a really nice chapter in the sense that we get to say what all these limits were really all about primarily. It's needed to define the derivative in the first place. So we'll get to say, what do we even mean about the derivative? The short of it is we're thinking about slopes whenever you say derivatives, so rates of change. But we'll discover how all those ideas connect very carefully once we get to chapter 3. Here in chapter 2, we're just on the last example with continuity. And our new quiz that's posted here, this one is relative to section 3.1. So if I feel like we don't get too far on this, I might change the due date and push it back next week. We'll just see where we end up. So that's where we're at so far. And if we're looking ahead to the further out schedule, not a whole lot's going on with these weeks. Just a reminder, midterm week is coming up, but there's no exam, there's no special project or anything like that on midterm week. This will just be an opportunity to say what your standing is in the class halfway through. Then we'll have our exam right after. Didn't quite make it to midterms week. So that's where we're at so far, folks. That's where we're going. Let me move that back where it was. Okay, any questions before we get started? Okay, let's dive in. So I have to clear this out. There we go. So this is the last example we were taking a look at right before we got into, oh, sorry, I didn't have my windows quite right. Let me fix this real quick. There we go. So this is right before we ended class on Monday. Here we're using continuity to evaluate the limits. And this is something that didn't work out every single time in section 2.4 because we had problems where x was heading towards. Oftentimes x towards 0 was a value that might have caused a division by 0, for example. And so we had to do some kind of simplification with the function in order to actually use continuity. So section 2.5 is just giving us the punchline of a closer look of how those limits were really going. None of these actually needed any extra algebra. We just used continuity on every single one. I believe there were some corrections we had to put in here. So after some corrections were put in, for example, in part B, if the limit is heading towards 0, through continuity, we're just putting in 0 for x. So here it is, 0 squared. And then we just simplified it down. We got a 2 on that one. Again, on this one, I forgot to put the arrow there. So just to emphasize a little bit further, by continuity on this, it's a really long word. There we go. We have a rational function. The only way this would go awry is if x was heading towards, say, -1/5. Then we might have a problem with this one. But if x is heading towards 4, we just plugged 4 in for the variable. Now we just have a huge order of operations problem, and we got 22/19 on the limit for that. So continuous functions are great. There's not a whole lot going on in the limit. You're just doing a direct evaluation. Any questions at all, folks, with how those kind of limits go? Okay, this also means that when continuity comes up on exam 2, limit questions like these are not going to be too involved. They're pretty fast to get through. And here's the last application problem we have on these notes here. I notice I didn't take the best screenshot on that. Let me see if I can make it bigger. Making it bigger doesn't make the resolution better, but sorry about that. I'm going to try and make sure I get more high quality screenshots on these things. But here's what's going on with the application. Just a good way to see when continuity works, what happens when we have continuity breaking. It says here, a patient's injected with a drug every 12 hours. So that's why we have the scale here. Every 12 hours, something changes. So T for time makes sense. We have to understand what's going on with the vertical axis, C. It says further, the graph shows the concentration, C at time T, so C of T, of the drug in the bloodstream after T hours. So this function in blue is just, we could call it C of T. It comes in 4 different pieces. I guess after the 48-hour mark, the patient was done with whatever the infusion was or the injection therapy. But C of T is this whole function here in 4 different pieces. They're asking us at what values of T does C have discontinuities, and what types of discontinuities does C have? Well, certainly we have discontinuities at 12, 24, 36, 48, because if you were to try to plot this, you would have to go here with your pen or pencil, put it in a circle, and then the fact that you have to jump up means we have discontinuities. So let's write out there are discontinuities at time T equals 12, 24, 36, and 48 hours. Then the follow-up question is asking, what type of discontinuities are these? Any volunteers for the type of discontinuity? Exactly. They're all jump discontinuities. Let's put here. These are all jump discontinuities. And well, that kind of ends the problem. This is just a different way to see a graph in an applied setting, what it might look like. And there's a lot going on with this. When it says the graph shows the concentration, C of T, of the drug, this is really just a model of what the concentration would be in the person's body for whatever that drug would be. It may not be true that this is the most accurate graph. Maybe something more accurate could have been something along these lines. At around 12 hours, we have a concentration that goes like this, and then we want a surge function that comes up and around and then comes down, another surge, and so on. But we have to make sure that this is defined in a way that doesn't violate the vertical line test. That's why this model would be really complicated. But the one that's actually provided with the real discontinuities, this model is just a little bit easier to work with. It's not a full match of reality, but we'll say here, this is a model which approximates the true concentration C. Now we'll look at other related models as we go through the course, particularly in chapter 3. We'll see how we can better model this kind of situation with pharmacokinetics. But this was our last topic we had to take care of after Monday's class on continuity. Any questions at all, folks, on the conclusion of these notes or this problem? Okay, let's save this up. We'll get this uploaded onto the Moodle website. But for now, let's go and turn to chapter 3. Oh, let me pull that out. Sorry, I have a participants window on the right that you can't see that hides my folder that I think you are always able to see. There we go. Zoom makes things just a little bit tricky to work with, but we always get through it. So finally, we're in chapter 3 on derivatives. We have hinted at what they might be, but we've never really brushed up against them just yet. Section 3.1 is, again, defining the derivatives and rates of change. And it starts off with this pretty esoteric looking definition. It says the tangent line, we need to define that in our graph that we're going to put down below, to a curve y equals f of x at a point, a f of a, that's just a point on the graph. The p here is kind of curious. You could have just said the point a f of a, but oftentimes the book like to be specific and write out this way, is a line through p with the slope given this way. So already we have kind of an inkling of what's going on in this section. If you're talking about derivatives, what that really is all about is a slope. And there's the slope m, but it's defined in a really weird way. And notice it has a limit right in front of it. That's, again, the major justification of why we're doing all that work on limits in chapter 2. So if this limit exists, that's the slope of the graph at the tangent line. But what we need next is produce some graphics to show what all this really looks like. When you're reading this in the textbook, they already just display the graphics for you, and they say, this is what it looks like. But those graphs are extremely busy. There's a lot of information. Sometimes the better way to understand a definition like this is to build it out ourselves so we can see step by step each component. So first thing I'm going to do is put down a quick graph going this way. I'm emphasizing quadrant 1, not because it's required, just to make it a little bit less busy when we go to draw this out. We need a curve y equals f of x, so let's start there. I'm going to plot that just in black so we don't have too many colors going. Let's see, I want to make it go about like this. So some strange function, here's y equals f of x. So we have that part of the definition down. Next, we need to put in a point a f of a. So let's put down a point here. On this graph, that'll be my a value. It produces a point right in this location when we go up vertically. Oh, and now over here, that's going to be the output, or the second coordinate f of a. So here's f of a going over here. So now that we have a curve, we have a point a f of a, we need to produce a tangent line. So a tangent line is a really interesting concept. I'm going to graph this a couple times. Let's zoom in as well to really focus on what we're trying to do. When we put in a so-called tangent line, well, that's too much of a zoom in. What we're trying to do is approximate the function right at that point as best as we can possible. In other words, we want a line that comes through. Oh, that's not quite right. Let me try again. A tangent line has to touch it just like that. That's not too bad, but let me try one more time. Let's get this one as good, as nice as possible. When you're trying to put in a tangent line, you want the slope of the tangent line to be about the slope of what you would expect it to be in that location if it were a straight line. So let's try one more time.
Yo.
Sorry, question first, Eli. Okay, so that will be my tangent line right there. Any questions at the moment?
I was right there.
Sorry, Eli. I'm not sure if you have a question or maybe it's just an open mic. Or it could be internet lag. That's always an issue we have to deal with in this class. Okay, looks like we're at this part now. We have a tangent line produced. That's this line right here. But let's say a little bit more about that. If you take this picture right here and blow it up, what you should see is, with a high level of zoom, is that the curve looks about like this, and that the tangent line looks just about the same. It'll differ on the fringes when you go really far out. That's what we're seeing out here and way down over here. But locally, right at that black point where the red dot is, if we have a real tangent line, then zoom in, and the curve in black, the line in blue, are going to become indistinguishable. So it's in that sense, sometimes the tangent line is called the best local linear approximation. Let's put that in just because we said it. The best local, by local we mean only around A are you going to get a good linear. Linear because it's an actual straight line. It has an equation y equals mx plus b. approximation. I'll abbreviate that to approx. So that's what the tangent line would look like. Still, lots going on in this picture. Let me remove this so that it doesn't get too busy. So we have a tangent line to the curve at the point P, AF of A, that's this point right here. It's the line through P. It did go through P, so we're on the right track. With the slope given in that way. So now we need to understand that limit expression. But even before that, let's focus on just the slope M. It's that right there on the tangent line. The slope of that tangent line would match this limit. So let's see how you would calculate it. First thing we do is probably write down the equation for the slope. So M would equal y2 minus y1 divided by x2 minus x1. And notice already, we have a really major problem. Anyone see the difficulty with finding the slope of y equals mx plus b, that blue tangent line, using that formula? What would go wrong if we attempted it? We have some chats coming through. Exactly. There's an A here, there's an H there. So there's some confusion going on with the denominator for sure. And there's another really big difficulty. So let's say, what is x2 and x1 to try to bring back what is A and H? So over here, here's our A. We're thinking of that as being x1, but then where's the x2? If we're using just 1 point, x1 would be equal to x2, and then you've divided by 0 in that denominator. The slope would not exist. So that's our major difficulty with coming up with the slope of a line. You actually need 2 points, or else you're dividing by 0. So we need to get around it with that, and we need to produce a second point. So here's our second point we're going to throw in. Let's go to a new color green for this. So if I want a point nearby A, which we're calling x1, just using this formula, we might call it A plus H. The H here is just a slight increment to move the point away so that we can actually have 2 points to work with. Now the formula appears on the table. So A plus H is a location here. On the graph, we go vertically upwards, and we hit a point in this location. So that point has an output on the left. Let's go over here. This is f of A plus H on that coordinate. Got a little tight over here, so we'll use the arrow trick. And now here's the next issue. If I use that second point, we're not actually producing a tangent line any longer. What we have is what is called a secant line. So let's zoom in on this again and draw this out carefully. The secant line connects with the point in question. We wanted the tangent line at A, but it's also going to have to connect through this point at A plus H. So it looks like this. Comes up and around, down and out. And notice the lines are pretty close. They would get even closer the smaller and smaller H goes. So if you take the limit as H turns to 0, the lines would actually overlap here. But for the moment, we need that second point just so that we can calculate that slope. And we'll call this, let's see, find a good spot to put it in, the secant line. I just need to try to make this not so busy. How about right over here? Secant line. So we have the secant line. That's not the one we're interested in. We're interested in the tangent line, but at least we can come back over here on the slope and start filling this out. So let me find the right level of zoom. Let's start putting in values. One thing that's kind of tricky about the slope formula is we have y2 and y1, but those are actually the function values here. So we'll say, just for a quick reference, f of y2, that's the second point. Or excuse me, let me say this in a better way. Sorry for folks working in pen. Let me say this as y2 coming from over there equals that point, f at A plus H. y1, that's just the first point over here. And that one we're labeling as f of a. We're emphasizing the function notation. So y1 equals f of a. Down below over here, a was x1, but let me just move that label over a bit. A plus h is x2. So now we have everything we need to fill in the slope formula. On the next line, m turns into, first it's this f of a plus h. That's coming from y2. Then minus f of a. That's coming from the second coordinate here, so the y1. All of it's going to be divided by, we go take the x2 value. x2 is a plus h. Notice it's the same thing that's inside the function notation. It's just carried down. Then we go minus f of a, or excuse me, x1. x1 down here is just the a, or you could see it by pulling it out of the f of a like that. So that's just using the slope formula. Just to convey a little bit more, this y1 was the f of a, which was that right there from that second point. So it's the difference in the y values, f at a plus h minus f of a, divided by the difference in the x values, a plus h minus a. But then that gives us a cancellation. We have that m equals f at a plus h minus f of a, all divided by just h. But one thing I should have done at the very first step here is I'm writing m equals, but let's put in an emphasis here. It's really just approximately equals on every single one of these, because we want the slope m right here where it's highlighted in yellow. We found the slope of the secant line, and that's not good enough because it's just slightly off. They are sloping by different amounts. So approximation symbol is a good reminder here. The only way to make this approximation even better is we have to take that h, make it smaller and smaller. That means that little tick mark is going to move over to the left towards the original one, right at a. But when that happens, this part of the graph is going to start moving. That dot moves over here. It can never actually overlap, but that's okay, because when we take the limit as h goes to 0, what happens with h is 0 itself is not what's relevant to the limit. This one is not going to have direct substitution whatsoever because you can't put 0 inside there at all. So we have to do a little bit of algebra to clean up the limit, like in section 2.4. Let me scroll up a bit there so we can see what we're looking at. Sorry about cutting off the top of that. So at the end of the day, the only way to make that an actual equality is we write out this. M, which is the slope of this tangent line following the yellow color coding, the tangent line in blue, is the limit as that h down there goes to 0. This is a double-side limit, so we don't say from the left or the right, just goes to 0 in total of that thing, f at a plus h, minus f of a, all of which is divided by h. So that's our formula right there. And we're going to say very soon in these notes that this is the derivative, which has a name. We'll call it f prime at a. So we have the original function, f at a, no special symbols around f. But if we're talking about a derivative, we put in that little fancy symbol. It's not an exponent, so it's going off in an angle, and it's just read as prime. That's how we indicate we're talking about that slope there. So this is the process of defining a derivative. It's all about getting a slope with exactly 1 point. And that's a pretty neat trick because we've been told pretty much all our lives in an algebra class, it's impossible. You need 2 points. Well, that was kind of a lie. You can do it with 1 point if you have a function like this and you're taking a limit. That was the extra information you just don't normally bring to an actual algebra class. Well, any questions at all, folks, with this definition? Okay, what I'd say we have to do right away is use it in an actual example. So that's what I have down below in the notes, 2 examples where we're going to calculate this limit. And even though the problem doesn't ask for it, we'll also use the good old Desmos graphing calculator to actually plot the original function, the secant line, and see if it's convincing. See if we zoom in right around here, if the tangent line in blue really is the best local linear approximation. So here's where it's going to start out. So here's the definition, just repeated so we can refer to it as we try out this new example. Example 1, part A, I could have saved some space by moving that up, says consider this curve, y equals x cubed minus 5x plus 6. We want the tangent line to that curve at the point 1, 2. So let's start breaking this down. Here's what the problem looks like. Here's the definition above. Very first thing we'd want to say is, well, the definition talks about a curve y equals f of x. This is very common in calculus. Function notation is being used everywhere. No f of x in sight here, but what you can always do is just say f of x or y equals f of x, which is the x cubed minus 5x plus 6. So in other words, if you have just a y equals, you're always welcome to assume that that y is the f of x function used in this definition here. So that's our first start. Now we know we're taking the limit as h goes to 0, but then the next confusion is we need to know what a is here and here in order to do that limit. So reading through this information here on example 1, the only way we're going to get the value a is if it came through a point, the point a, f of a that's being referred to, and they did give us a point, it's 1, 2. That tells us that's our a value right there. So a equals 1. They also gave us a little bit more. The second part of the point is f of a, which is 2. So that's telling us that f of a is f of 1. Let me fix my penmanship there. That's getting kind of sloppy. If I can't read it, I know I've got a problem with it. F of 1 has to be 2. But let's double check. When we say f of 1, that means we're plugging 1 here and here. It would turn into 1 minus 5 for a negative 4, plus 6 does give us our positive 2. So we've got the a value down. We know the function. We just need to put it all together and write out the limit. So here's where it begins. M equals the limit as h goes to 0 of f at 1 plus h. So I inputted the 1 into this location minus f of 1. So 1 went inside here as well. Oh, that red dot was moving around a lot. All of which is divided by h. So we've done a lot of works on limits in chapter 2. All that work was to help us support us getting through these kind of problems. Any questions at the moment, folks, with plugging in the value 1? Okay, here's where another nice strategy can help us out. Sometimes the limit statement here can get pretty big and messy. And oftentimes due to this one part right here by the red dot, f at 1 plus h. So let's use the method of just divide and conquer. Let's look at f at 1 plus h, calculate that, and then we'll just plug it right back inside here. So we'll come back to the limit after we figure out what this is all about. We're using function notation, and in function notation, the 1 plus h would go here and here. It's unfortunate that the power is 3, but in the web assigned homework, I had a hard time finding an exercise with the power 2. So we're doing one very similar to the homework. So if that's power 3, this all turns into 1 plus h cubed minus 5 times 1 plus h plus 6. So let's scroll down and just start cranking this out. 1 plus h cubed just means take 1 plus h times 1 plus h times 1 plus h. Then I'm just copying the rest of it, minus 5 times 1 plus h plus 6. Now we need to expand all of this. We need to FOIL it all out. And oftentimes you want to just focus on 2 terms at once. I'll put a bracket here to say, I want to expand that expression. We'll FOIL that out. get 1 plus h multiplying. First 1 distributes through, it's 1 plus h plus distribute this h through, we'll get h plus h squared. I guess we can distribute that -5 through while we're at it to get minus 5h. Oh, let me try again. I mean, it's good to go in order. Minus 5 times 1 is just -5, then minus 5h plus 6. You don't have to go in order, but the notes get confusing if I switch the order on those. So let's simplify that bit a little bit further. 1 plus h is now multiplying. I'm going to take the brackets and just demote them to a parenthesis. 1 plus 2h plus h squared. We have like terms on the right, so that's 6 minus 5 for plus 1 minus 5h. So it's coming together, one last distribution through. Now we're doing a binomial into a trinomial, but it's the same kind of business as normal. First distribute 1 into the group through the right. That's just multiplying everything times 1, so we get 1 plus 2h plus h squared. Next, we're multiplying h into that group, so we get plus h plus 2h squared plus h cubed, then plus 1 minus 5h. Gigantic mess of stuff, but all of that, once we have it all cornered here, it's just going to be substituted into that location. And even better, we know what f of 1 is. It's just the second coordinate 2 that we indicated right here. So now everything just goes right back into the limit, and we're going back to chapter 2 techniques to calculate it. Any questions at all, folks, before we go and just put in that value for f of 1 plus h? Okay, so here's the algebra stuff. This happens a lot in calculus. Sometimes the algebra gets a little bit hairy, but go slow, methodical, and you'll be in great shape. If you notice I miss a term or anything like that, let me know right away, and I'll try to correct it. I noticed I didn't combine like terms. Let's maybe take that extra step to make it a little bit less confusing. There's a 1 here and a 1 here, so we really have 2 plus 2h. Oh, and let me try again. There's a bunch of like terms, aren't there? So 1 and 1 here, and then 2h. And h gives us 3h. We have h squared plus 2h squared, so plus 3h squared. Oh dear, plus h cubed minus 5h. When I looked at these two, I missed the negative 5h there, so a little bit more algebra, and we have 2. 3h minus 5h gives us negative 2h plus 3h squared plus h cubed. I should have looked at that sooner on this step. Loads of like terms. Always good to simplify these things first as much as possible. It just makes our life easier in the limit. So I think that's the best simplification of f at 1 plus h. Any questions or comments at all, folks, on cranking that all out and then simplifying it? Okay, let's return to the limit above. All of this is equal to the slope m, but I'll just use equality to carry on. So long chain of equality is going to tie back to the original slope m of the tangent line. This is now equal to the limit as h goes to 0 of probably a pretty big fraction. So let's start off like that. Hope it works out. I'm going to put a little border here just so that we can separate the scratch work on the right. F at 1 plus h settled down to 2 minus 2h plus 3h squared plus h cubed. Then we go minus f of 1 here. That came out as a 2. So just minus 2. That was a little bit dramatic on the fraction part, I'd say. So that all came in kind of nicely. More like terms that we can take care of. This positive 2 and that negative 2 cancels. And thank goodness, because the only way to do this limit is through continuity with direct substitution. But this function is not continuous at h is 0. So our goal was to cancel that h right there in the denominator. Every time we do this problem, that's the goal. Cancel that h. So you can use direct substitution. The moment negative 2 and positive 2 canceled out, all the terms have nothing but h left over. And that means we can cancel h. I'm going to take the extra step and write out this way, as our author often does. This is now limit. Let me move that cursor somewhere that's not distracting. As h goes to 0, with all the terms left over here, they all have a factor of h, so we'll factor h out, leaving behind negative 2 plus 3h plus h squared. H is down below, and so here's our cancellation. H's are gone, but once that h is out of the picture, we can take the limit as h goes to 0. This is just direct substitution. 0 goes in here, and so that means this goes to 0, that goes to 0, but you know what, that looks kind of messy on this line. You're welcome to do all that in one step, but for the sake of the notes, let me write this out once more, just so we can visualize it better. So now the limit as h goes to 0 of negative 2, we don't need a denominator any longer, do we? Let me try again. Negative 2 plus 3h plus h squared. This will turn into just negative 2 plus 0 plus 0. This is just to convey that we use direct substitution, got a 0 here and a 0 here, because it's a limit as h goes to 0. And so finally, all of this is negative 2. We want the equation of the tangent line to the curve y equals x cubed minus 5x plus 6. But this is the big half of the battle. We found the slope. It's negative 2, so now we're able to finalize this problem. Any last questions, folks, before we go to the tangent line equation?
Yeah, I was just wondering, as we were going through simplifying the problem, where did the negative 2 on the end come from? It's like the top of the 3 limits on that left-hand side. Yeah, that one.
Yeah, so this negative 2 came from minus this f of 1 right here. And then the f of 1 came from that second point. So the point was 2. So f of 1 came out as 2. But a different way to see it is when you see that f of 1 there, you're really just plugging 1 into this location. So there's really 2 ways to think about it. Plugging a 1 here would give us 1 minus 5 for a negative 4 plus 6 coming out to that 2 right there. So that's how they kind of connect.
Okay, thank you.
Yep, absolutely. Thanks for asking about that. Other questions at the moment? Okay, I'll leave these arrows here if you're a fan of arrows. I kind of am, just to show this is pretty much the process for this style of question. If they give you points like 1, 2, then you can guarantee, unless the problem is completely flawed, that this one is the second coordinate. Negative 2 just because the negative sign right in the middle there. Other questions at all, folks, with the limit? Okay, so this is the hard step. The next step is just kind of a review of algebra. What we need is the point. So let me just rewrite m equals negative 2. The point was given right here, 1, 2. I'll call this x1, y1 equals 1, 2. And now we just use our favorite equation. There's multiple ways to go for building the equation of a line, given a slope and a point. I would usually almost always go this route. I like this equation, y minus y1 equals m times x minus x1. This equation has a name if you're curious. This is called the point slope equation for a line. So in using this equation, we have x1, y1 indicated, a slope m given. So this becomes y minus, in place of the y1 here, just drop in a 2, equals the slope m. That's the thing we painstakingly calculated. It came out as a negative 2, multiplying x minus x1 is a positive 1. So now we have a good equation for the line. It's pretty standard for this kind of equation. We want to put it into slope-intercept form, but that's just another way of saying solve for the y variable. And that makes sense because if you're doing a check on this problem, solving for the y variable is pretty much required then. So next steps, we'll have y minus 2 equals negative 2x plus 2, just distributing the negative 2 on this step, then add 2 to both sides, and we have y equals negative 2x plus 4. And my claim is this is the equation for the tangent line. Well, that's the claim. At here, this is where the problem would end, but we'll add a little bit more just to see, does it even make sense? What did we even calculate? And does it look believable as a tangent line? First, any questions at all, folks, with getting this equation down here? Okay, let me put down below just on the notes. Let's type out, guess we're going to go to another page for the check. So this is the check on the last example. What we really need is some graphing software, so we couldn't do this in exam setting. But while you're learning this, doing it WebAssign or doing a quiz problem, technology like this is absolutely on the table. It's a good opportunity just to get an extra look at everything. First thing you want to plot is the original function. So we scroll up to here where it's given as either f of x equals or y equals, your preference. I'm a fan of function notation, so personally I'd probably go f of x equals x cubed minus 5x plus 6. Now we get a weird graph, but we have to keep in mind, we're only interested in the point when x is 1. So where x is 1 would be, let me zoom in on this a bit more, right about here. Let's see. It's really hard to settle in. Hey, there it goes. There's the point 1, 2 that we were given originally. So at least we know the point 1, 2 is there. If we were to attempt to draw a tangent line, it would look like this. Here's the point 1, 2. The tangent line equation I claim should look like that, meaning it better have a negative slope. The slope is negative because the curve is going down in that way. So let's come back over here and now put in our equation of the tangent line. It came in as negative 2x plus 4. In Desmos, you can just click down to the next line and put in y equals negative 2x plus 4. And there it is. That's our tangent line that we were looking for. So my claim is this line in blue, let's blow it up for just a moment, is the best local linear approximation to the original curve, the one in red, at the point 1, 2. If that's the case, you should be able to zoom in on 1, 2, right where the red dot is, and both curves should look indistinguishable. So let's give this a try. Zooming in to start. After a while on this zoom, you'll start to notice that the red and the blue start to just overlap on each other. Right around this level of zoom, it's hard to even tell the difference between the two. Differences over here, we're moving away from 1 when we're way out here. So we're finding that the curve, the tangent line in blue and the curve in red are different. But right around here at actually 1, 2, totally indistinguishable. So in this range, this is a terrific local linear approximation to that nasty function. Why do we like linear functions? It's because if this was, say, an applied problem, if there's more going on, and we had to do further work with that function, maybe there's a lot of functions like those are really difficult to work with. But if all we care about is right at 1, then we can use the linear function, and notice how much simpler it is. Something complex, if we're only caring about right around 1, 2, this point, can become something very, very simplified, negative 2x plus 4 in an approximation. Oh, didn't mean to zoom like that. That's a zooming on Firefox browser or Chrome browser. Let me fix that. I just want to put this picture back to about where it was, and we'll leave this as a screenshot. But any questions at all, folks, with the graphics here? Okay, let's see. It's kind of hard to find a good window to put this in, but let's make that our graph right here. maybe just a little bit more of a zoom out. I'll put the actual, oh, let me move the red dot first. I'll do a screenshot that goes like this, so you can go to that web address if you like. And this is what it would look like putting everything in if you're double checking on your own work. So there it is. And another thing you can think about, by the way, is what did we really calculate? How does this apply to, say, a real world situation? If you say that this was time, t in hours, say, and this is distance, say in miles per hour, then the slope m is a rate of speed in miles per hour. So in other words, imagine driving your car. The moment you look at your speedometer, it's essentially an approximation like this, an instantaneous rate of change, giving you that actual speed. So that's what your derivative is, the speed that you see on your speedometer as you're driving your car. Well, another look at this is, what if we got the wrong thing? Maybe our slope was wrong, our intercept was wrong. This is a really powerful check. You would tell immediately right away. And let me show you why. If we had something other than -2 right here, this nice picture of a tangent line is going to become obviously not quite right. So let's say if it was positive, well, the curve is connecting here. That's not quite right. If we got negative, but it wasn't quite -2, maybe -1.99, it looks pretty okay to start, but let's zoom in on that. There is exactly one correct tangent line, and my claim is that one's not right. Zoom in right here, and we might be able to see why. Notice what happens. The more we zoom in, the curves are actually moving further apart. This is not a great approximation at all, and it was only off by 1/100th. So this is a very sensitive process to get it just right. Well, that was our first example along those lines. We took a lot of extra time on it because, I mean, it is tricky to see what's going on in the algebra, the actual limit. This is just a review on getting the slope of the tangent line. We'll do it a couple more times. But it's also important to see this picture as well, because it reminds us what we're really trying to do is always this process here. We're calculating the slope of a line, the y equals f of x in black, relative to 1 point. That's the rate at which this curve y equals f of x is increasing, or your speed in miles per hour is changing right at this one instant of time. Well, that's a lot of stuff going on, so we definitely need to try another example along these lines. Any questions at all first, folks? Okay, well, let's try this out again. Same kind of setup as before, but new equation. This time we have a square root type function, root x plus 5. Very first thing I'd want to do with that is just say, let's call it this way, y equals f of x is the square root of x plus 5. We've done limits involving square roots before, so if you're thinking conjugates might come up, good on you. That's exactly what's coming up for this kind of problem. But really the very first step that I encourage you to take, essentially each and every time you do this problem, is write down the formula for the definition of the derivative. It goes like this. If we want the equation of the tangent line, oh, didn't mean to draw on it. Let me start over. If we want the equation of the tangent line, the very first and most important thing we really want is the slope m. It's a limit, so definitely write this down. Limit as h goes to 0. This is a formula that comes up in different settings, so we'll have to use it a lot on exam 2. F of a plus h minus f of a all over h. So that's funky looking h. I think I can fix that. There we go. Still a little bit weird. I don't know what happened to my h's today. Maybe too much coffee. So once we put that down, there's still a lot of questions. Anyone spot what the value is for a on this problem? Good call, Emily. It's always that first coordinate, -1. So we'll put -1 in here for A. Once I get that eraser going, there we are. So A in this problem is -1. And that means f at A is really just f at -1. Two ways to calculate it. It means you're plugging -1 here. That'd be the square root of 4, which is a 2. But you can also just always grab it from the second coordinate. The second coordinate is the function value when we're looking at a pair of points like that. So we have A value is -1, f of A is +2. So we'll throw a 2 right here. And next we'll go, this is equal to the limit as h goes to 0 of f at -1 plus h to start, minus 2, where we plugged in the function value right there, all of which is divided by h. And just copying the process, what we did in the last problem was we took this right here, and we just calculated it carefully. F at -1 plus h. This time the computation is not too bad, but we're just practicing function notation, essentially, putting it on the right here. If you did it all in one line on this problem, I think that's probably just fine. But f at -1 plus h means we go back to the f function. Here it is. And we're plugging in -1 plus h in that location. So it turns into square root -1 plus h plus 5. That means it's the square root of h plus 4, one simplified. So this quantity here, that expression gets dropped into that location where it's highlighted. So let's write this in. It's now the limit as h goes to 0 of square root h plus 4 in the numerator by substitution, minus 2, all of which is divided by h. So we're back into that same similar situation that we deal with all the time in section 2.4. We want to take the limit as h goes to 0, but you cannot directly substitute in 0 for that h right there. We've divided by 0. It's completely undefined, but the limit still may exist. So here we go and change gears. To cancel that h, we need the conjugate. By conjugate, what we mean is we take the thing in the numerator, we write out again, but we interchange the sign, whatever it is, to the opposite sign. So negative there means we'll go positive. So we'll have root h plus 4 plus 2 divide by the root of h plus 4 plus 2. Now we have to expand all this out. In the numerator, we're fully foiling, so parentheses just for an emphasis. In the denominator, I would almost never distribute this h into a group. Let me say that again. I would never distribute the h in the group. I think that's usually a bad call, because if you want to take the limit as h goes to 0, you need to cancel that h. It's better just factored out right where it stands. So I'll put parentheses here, but I'm just going to multiply them together without distributing. So next line, we have limit h goes to 0 of one huge fraction now. It gets a little bit worse before it gets better, but it cleans up really quickly on this problem. We're taking h times the group, root h plus 4 plus 2. Now let's start the distributions in the numerator. First, I'm multiplying this to this. But if you take root h plus 4 times the root of the same quantity, the square root falls off and it's just h plus 4. Next, it's that times this. So 2 plus 2 square root h plus 4. Now we're changing gears. -2 multiplies here, so minus 2h plus 4. Excuse me, minus 2 square root did h plus 4. And last one, here to here, is just going to be minus 4. And notice that's kind of a mathematical miracle in a sense. These are terms that don't involve h whatsoever. They have to cancel. That way, this h isn't canceling across addition or subtraction, and it's a legitimate algebraic cancellation. So let's put in this cancellations. Positive 4, negative 4 are gone. The roots in the middle have opposite signs, so they go away. All that's left is that h. If you canceled it right here, no harm done. But I'll take that extra step just to make the notes a little bit more readable. We're landing on limit as h goes to 0 of just h above, all of which is divided by h times the root of h plus 4 plus 2. So here's our big cancellation. Once that's gone, direct substitution is now on the table. We can use continuity. I like to put in a 1 here because sometimes I forget that this is a fraction and it has a numerator of 1. I made a mistake where I just copied the denominator after that kind of cancellation. So now this is limit as h goes to 0, 1 divided by root h plus 4 plus 2. Finally, that's a continuous function at the value of 0 for h. So we'll just plug in 0 there and get that this is 1 over root 0 plus 4 plus 2. So that's just the square root of 4, which is 2. That means it's 2 plus 2 in the denominator, and we get 1/4 altogether. Now what we've laid out is one big trail starting at m, that's the slope. Through the transitivity of equality, the slope is now that. So that's nice having a big line of equalities, but sometimes it's not a bad idea to just summarize. So I'll say down below, by this work, m equals 1/4. We also want the point, x1, y1, which was, let me zoom out just a touch there. Touch again, a little bit more. The original point was -1, 2. Well, any questions, folks, to this stage of the process, getting the slope out? Okay, fantastic. We're pretty much on our way. Again, we're calling this a slope, but what it really is the derivative. So this could also be paraphrased by saying f prime, the prime symbol right here indicates the derivative. It's the derivative at a particular x value, but that would just be the -1 coming from there, equals 1/4. So this is the derivative of f at that -1. So that's a lot of work to get that out, but maybe not as bad as the last example. That last example just had problems with raising something to the power of 3, making the algebra go out of control. From here on out, all we now need to do is just write down any equation you like for the line. Point slope equation goes y minus y1 is slope m times x minus x1. Our y1 value is the 2. x1 value is the -1, which means we need to contend with double negatives. And we got our slope, 1/4 in that location. So this will turn into y minus 2 for the y1, the second coordinate here, equals 1/4 from the slope, multiplying x minus -1 from right up here, coming from the original point. So we'll simplify that down and get a tangent line. So we could call this y minus 2 equals, fractions are kind of inconvenient, but no big deal. We'll distribute through. It'll be 1/4 times x. This is actually a positive one with the double negation, so it's 1/4 times +1. So plus 1/4. So now finally, this -2 we can rewrite if we'd like and call it -8/4. Still, it's a -2, but now it's compatible with a 1/4 over here. So add +8/4 to both sides. Y is going to be 1/4 x plus 9/4 after adding that 8/4. So this is finally what we wanted. This is the equation of the tangent line. Deserves an exclamation mark because that's a lot of work to get through. And we'll double check this one as well while we have time. Any questions at all, folks, though, with finalizing this problem? Okay, this is the moment of truth. Let's see if this is really accurate, if it's a real tangent line. Sorry for covering that up. First thing to do is put in the original function. Forgot what that was, so let me go up. Original function is square root x plus 5. So f of x equals sqrt will give the root x plus 5. Let me just double check that's right. I already forgot. Yes, x plus 5 there. Then come down to our work where it ended here and plug in that final statement. First, let me get this to a decent zoom where we can see everything. There it is. It's the square root of x plus 5. Original square root function looks like this, just a root x. But if you go plus 5, the whole graph goes left by 5 units. That's always weird in algebra how that goes. And now here's our tangent line equation. Y equals 1/4 of x. Looks like you could have the right slope. Let's add 9/4 and see if it becomes a tangent line. So plus 9/4 gives us this picture right here. That tells us, yeah, once again, here's the point -1, 2, the original point of the problem. The curve in purple and the curve in green match up to a high degree right at this location. If we zoom in more and more, we need to see both of the lines suddenly overlapping, becoming collinear, the closer and closer we zoom in. And that's exactly what we're seeing in this picture to a high level of zoom. There's no apparent big difference between the function, I don't even remember what the color was, and the tangent line, which is purple now. Well, any questions at all, folks, with the check or the original problem? Okay, just for the sake of the notes, let's put in one more screenshot. I mean, this is only the second time we've done this, so I think that helps out. So here's what the graph of the situation looks like. And before we do example 2, let's spend a little bit more time on this screenshot to just see what's going on to help us out solve example 2 as well. Let's put a quick border there. So we have two functions. Here's the one in green, that's the f of x. We have the one in purple, that's the tangent line equation. And the point in question was right here at, I forget, I think it was -1, 2. So that would be right here for -1 at a height 2. Yeah, that looks about right going by the grid line here. So here's the point, -1, 2. So special things that happen on this is, observe that at -1, 2, we can say that f at -1, you could plug it right here and get the square root of 4, which is 2, but you could also plug it right here, the actual tangent line equation itself. If you put -1 inside there, you would have gotten y equals 1/4 times -1 plus 9/4. That's -1/4 plus 9/4, 4 and 8/4, which is 2. So the function itself, you can find exactly one value to evaluate using just the tangent line and get the right function output. So f at -1 comes out as a 2 by actually using the tangent line equation to get that result. So that's kind of interesting. And lastly, this tangent line has, let's use blue for this. I think we've been doing that all along. It has a slope of 1/4. Because this line is in slope intercept form, 9/4 is the intercept. That means this right here is the slope, m. But m is extremely special if you're talking about derivatives. M means it's the derivative of the function. So we can now say m equals f prime, that's how we say the derivative, at that first coordinate, -1, equals, if we ever want to get the slope, and we have a tangent line equation, just grab that 1/4. So there's a lot of information to tie together with this kind of problem. Example 2 is just kind of a refresh on how this goes. There's a question just like it in WebAssign. So we have another tangent line, y equals 4x plus 5, another curve y equals f of x, but we don't actually know the equation of the curve itself. Nonetheless, we can do two computations. We can find f of 2, and we can find f prime at 2. Let's start with this one. This is the big deal for these notes. That's the derivative. F prime at 2 has to be equal to a slope. Anyone see what it should be in this problem? Just for a little additional hint on this one is the way we can get the slope from this equation is observing it's of the form y equals mx plus b. Oh, and I missed a chat. Let me grab that. Is it 4? Yeah, absolutely. Thanks for spotting that, Kaylee. The slope on this one comes from the form of the tangent line equation, which would be the 4 right here. So this equation, or excuse me, this example is really tricky in WebAssign, but that's just the reminder that if you have the tangent line, the derivative f prime is always a slope. We'll be repeating that almost like a mantra as we go through this course in chapter 3. If you always recall the derivative is the slope, it can get you through these kind of questions pretty quickly. So we took care of the derivative at 2. Now we need the function value at 2, but we just used the entire tangent line equation. That's what we were doing over here. Function at -1, you could either put -1 here or in the tangent line equation. We don't know f of x at this time, so we have to put it in the tangent line. And we'll say that f of 2 equals 4 times 2 minus 5. So that's 8 minus 5, giving us a value of 3 altogether. So honestly, example 2, it's not the most important question in the world. It's more just a concept equation to know that if you see a tangent line, you can always recover two things. You can recover the derivative when a is 2. Let's highlight that just to convey 2 is very special here. So you can recover the derivative at 2, but only at 2. And you can find a function value at 2, but again, only at 2 for this kind of problem. Well, that finalizes our example 2 here. Just a quick concept problem. With what we have going on next on the notes is we're just going to focus on more practice with derivatives. So down below, we formally define once and for all that word derivative. But when you look at this definition 4, it's essentially definition 1, with this being the major thing new. We're calling it the derivative of the function at a number a. We've been using blue for a while, so let's do that again. The derivative of the function at a number a is always indicated this way, f prime, provided the limit exists. And just for another reminder, this is always the slope of the tangent line. At x equals a. So what we're going to do is practice calculating the derivative f at a couple more times. And we've essentially done that before. The only thing that's different on example 3 is we didn't put in a number. Like on the last problem we had at -1, we were finding the slope of the tangent line. Prior problem, I think it was maybe I forgot, +1. Here, we're doing it for just a new variable, calling it a. By the way, this is pretty much what the quiz is going to look like. I feel like I didn't get far enough as I'd like to for this quiz to really be a fair one. What I'm going to do is push this due date back. So that's going to be due officially, we'll have it officially assigned on the 25th. It'll be due on October 2nd. That way you don't feel like you have to do a quiz on a due date if we haven't quite gotten to that problem. This is what the quiz looks like. I want to open it up just in case folks do want to start early. You're welcome to do so. So it's the same kind of problem we're looking at. It says find the derivative of f by using the definition of the derivative. The reason I put this in bold and the yellow highlighting is this is also an exam question. To get full credit on this kind of problem, when it says definition of the derivative, we mean this right here. This is the so-called definition of the derivative. So that's some really special instructions. I almost never do that in a class where I say you have to do something mathematically by that method and only that method for full credit. The reason for that is Chapter 3 is not as bad as it seems. 3.1, 3.2, it gets a little dicey, but we're going to find some really rapid formulas to doing this derivative extremely fast. Some people might know what it is already. But nonetheless, the limit definition is still extremely important. We need to retune these definitions for integration, for example. So the quiz is about knowing this as a concept. After that, we'll start doing these derivatives in a little bit of a faster way. This is a pretty tricky problem I have on this one, example 3a. So we'll probably give this one a little bit, or we'll leave this one for Monday's class next week. So we're not trying to race through it. Well, any last questions, folks, with our last 4 minutes? Okay, well, thanks everyone for your participation. When we come back, this is where we'll be in the notes, and then we'll probably get into section 3.2, 3.3 as well next week. Well, have a great weekend, folks. If you have any questions while you're working homework, don't hesitate to reach out. I'll be happy to help out. You bet. Thanks, folks.
What time are you coming back for your office hours?
My office hours start right at 3:30.
Okay, perfect. Thank you.
Yep, see you then.